let me just briefly talk about a couple of forces that you will be seeing a lot. I'll talk about the first three right now. So the first one that we'll discuss is weight. So all of you know what weight is. There's a difference between mass and weight, which I'm sure all of you are familiar with. Weight is the gravitational force on an object. What is mass? Mass is the amount of matter in an object. So the total amount of matter contained in an object is what we call its mass. And the amount of space occupied by that matter is what we call volume. So you can see that mass and weight are completely different because weight is just the gravitational force exerted on that object, right? So suppose you've got a ball or something up here, and this is the surface of the earth, then the ball will be feeling a gravitational force, right? We'll ignore air resistance for now. So the ball will be feeling a gravitational force in the downward direction. That gravitational force is called the weight of the ball. We can use Newton's second law to calculate that immediately. So we know the acceleration of the ball, right? The acceleration of the ball is going to be 9.8 meters per second square if there is no other force acting on it. So force equals mass times acceleration. Actually, it's F net equals mass times acceleration, but there's only one force here. So F net is just F. F net is just W. And then acceleration is G. So you can immediately calculate that weight is equal to mg, right? So weight should really be measured in newtons or force units. Though we use weight and mass interchangeably, and we often say that my weight is so and so kilograms or so and so pounds, but technically that's not correct. What we are referring to is mass. Weight is something that should be measured in newtons. All right. Another force that we're going to see a lot is called the normal force. Now, the normal force arises when you have an object that's sitting on a surface like this box, which is sitting on a tabletop. So the box is pressing down on the tabletop as a result of its weight. By Newton's third law, the tabletop will push back on the box. So that force which is exerted by a surface when you push against that surface is called the normal force. The word normal comes from the mathematical term, which means perpendicular. And that is because the normal force is always directed perpendicular to the surface. So another example would be, suppose you've got a slanting surface like this, and you have a box sitting on this slanting surface. So in this case, the direction of the normal force will actually be perpendicular to the surface. So Fn will be in this direction. Whereas the weight of the object will be straight down always. So the weight will be like this, but Fn will be perpendicular to the surface. So the word normal refers to the fact that this force is always perpendicular to the surface that's exerting the force. Okay, another interesting thing about the normal force is the following. So uh, as you're all sitting in your seats or when you stand up or lie down, you are aware of your weight, right? You have a sense of how much you weigh. Um, so where does that sensation come from? It's actually what you're sensing is the normal force. So why is that? So suppose you're standing upright and you have a sense of how much you weigh. So where are you getting that sensation from? Like your feet are on the floor, and the nerve endings of your feet are able to feel how strongly the floor is pushing back on you. And that is what you sense as your weight. So if you put on a heavy backpack, then you feel heavier. And that is because your weight is greater now, but the normal force exerted by the floor also increases because now the floor is pushing back harder on your feet. And that's why you feel heavier. So the normal force is what you perceive as your own weight. Okay, and also when you stand on a scale, the scale is really measuring the normal force. So you suppose this person is standing on a scale. The way a scale works is that there are springs inside the scale which get compressed, and the springs are calibrated. So by how much the spring is compressed, you can tell how much force is acting on it. That force measured by the scales in the spring is really just the normal force exerted by the surface, right? So when you stand on the scale, the force that the scale is reading out is not directly your weight, but it is the normal force. All right, another force that we're going to see very often is called tension. Tension arises when you have a cord or a rope that is connected to something. And let's say that somebody is pulling this end of the rope. So you're holding on to this end of the rope and pulling it. Now, we will usually assume that ropes or cords are unstretchable, and usually we'll just assume that they're massless, which means that they whatever mass they have is negligible compared to other masses in the problem. Now, when you have a unstretchable cord like this and it's held taut, a taut means like there is no lag in the cord, then what happens is that the cord is not happy about being stretched, right? It doesn't want to be stretched. And so tension forces will arise at two ends of the cord like this. And these tension forces are what's preventing the cord from getting stretched, right? So we're going to call these T. So there'll be two tension forces at the two ends of the cord. One technical point, which is not super important for us, is that the tension forces don't just arise at the two ends of the cord, they arise at every point in the cord. So if you just consider a very small section of the cord right here, this section is being pulled this way and also this way, right? So there are tension forces on every section of the cord as well, not just at the ends. But in doing problems, we'll only need the tension forces at the ends of the cord. So how do you apply Newton's laws? So this is a general framework that you can follow in doing all problems involving Newton's laws. The first step is that you choose a system and identify all the forces acting on the system. So what do I mean by choose a system? Well, if you have a very simple thing, like suppose there's one box and there are some forces acting on the box. Actually, whenever in this chapter, we are also going to completely ignore the spatial dimensions of an object. So if something is actually a box, there's no harm in thinking of it as just a point mass. So suppose there's only one object in the system, one object in the problem, then that can be your system. That is your whole system, right? If you have a more complicated situation, suppose you've got two boxes and they're connected by a rope, then it's up to you what you want to call your system. You can make the whole thing your system. And I like to put a dashed rectangle around my system just to clarify what I'm considering my system. You can take the whole thing to be your system, or if you want, you can also make one of the boxes your system, or make the other box your system. So that's up to you. You can choose whatever you want to be your system, and and what you choose to be your system depends on what the problem is asking for, right? So you choose a system, and then you identify all the forces which are acting on the system, right? We'll see examples of that later on. Okay. The next step is you choose a convenient set of axes and a sign convention. So you choose your x-axis and a y-axis. For each system that you have, you choose an x-axis and a y-axis in a convenient way, and also choose a sign convention. So you know which side is positive, which side is negative, and then resolve all the forces into components along those axes, right? So if you have an x component like this and a y component like this, and one of your forces happens to be in this direction like this, then you will have to break this force up into an x component along your x-axis that you're working with, and a y component along the y-axis that you're working with. Okay, so you want to resolve all the forces into components along these axes. And the third step is, once all the forces are resolved into components along the axis, you want to apply Newton's second law to each axis separately. So what you want to do is, you want to do F net equals mass times acceleration is what we are doing. Along the x-axis, this becomes F net x equals mass times the total acceleration in the x-axis, and F net y equals mass times the total acceleration in the y direction. And this will usually give you enough equations to solve for whatever unknown you are looking for. So these are the three steps that you follow in solving any Newton's second law problem.